one-man bands who propose their theory, and every few years they tend to change their theories, which makes things even more difficult. And conversely, very few experiments actually set out to test these theories. Many models fail to illustrate what they predict and or explain. And I've said this many times at these conferences, and I'm beginning to need to say it even more forcefully than once I did. And the worst thing of all is that almost every model, including all the models I've ever sustained personally, predict residual radioactivity of some kind. That's not to say that the author of these models predicts it, but if you read what their model, the basic physics of their model, they do predict it. So how do we go about testing theories? We can look for expected fuels and products, and helium-4, of course, is a fairly ubiquitous product from any kind of nuclear reaction, any class of nuclear reaction, I should say, including fission of uranium, of course, but and including fusion of deuterons. We could use chemical and physical or calorimetric methods, but they're not really very sensitive, and they tend to have a long time constant. Furthermore, the instrumentation to measure excess heat tends to shield the apparatus from nuclear measurements. So we don't expect too many lower energy gammas to get through a water flow calorimetry situation. To get around this, people have used CR39, isn't it, to examine particle tracks. And this plastic can be inserted inside an electrolytic cell, but even so, there is some shielding. We could use gamma ray spectrometry to measure gamma energies, intensities, and any decay rates if it needed decay. They might be prompt gammas, of course. We can look for isotopic anomalies by mass spectroscopy. The next question is it cold fusion? Fusion implies the approach of charged particles tunneling through a Coulomb barrier. I mentioned this problem just a few minutes ago. By far the most probable reaction is a proton and a deuteron producing a gamma and helium-3, as Conrad said. This reaction is about 14 orders of magnitude faster, given a constant distance between the nuclei as the D plus D going to helium-4. So if we're proposing that there's any helium-4 formed by deuteronic fusion, we expect 14 orders of magnitude more helium-3. And this implies, given that any heavy water or heavy or deuterium experiment contains a small amount of protein, but it's not 1 part in 10 to the 14, that the helium-3 reaction should dominate in all circumstances, because we can never purify heavy water to 1 part in 10 to the 14. So absence of helium-3, or that rather, the absence of dominating helium-3 implies no Coulomb barriers. And that is an extremely important conclusion. I think it might be compatible with your model, Jean-Luc, because you have an electron very, very close to a nucleus. So effectively, you have no charge on a hydrogen nucleus, and therefore there is no Coulomb barrier. So that's a way round this particular objection. So I praise your model. The next question, this question about the nuclear active site has been raised by a number of people, but particularly by Ed Storms. And I would just repeat that it's well established that chemistry, any chemical structure, temperature, pressure, and any physical conditions don't really change rates of nuclear reactions. Now, of course, this is not true in a fission reactor, where it's not the structure, but really the components present which are important. And there is a small variation of rate of fission based on temperature, for example, but they're rather minor effects, quite honestly. Furthermore, we notice that LEDA appears to continue in hotspots long after any melting. The hotspots are very large, and consequently, if the first nuclear reaction had caused a tiny bit of local melting, which you could not even see with a microscope, it ought to stop, but it continues, and the heat production continues in the same place. Now, the molten metal surely destroys any chemical or physical structure. So I think that the concept of a nuclear active site is completely wrong. Structures are not important. This is an example of a hotspot, and you can see it's about 100 microns in diameter, maybe a little bit more. This is on the surface of some nickel, and we made the Met Bell at the bottom right-hand corner as the Department of Metallurgy at the University of Bologna, B for Bologna. And this was made in 1996 in Stromanos's laboratory. Those strange granules at the center of the electron micrograph is actually a eutectic of tin and nickel. At the time, we had no idea how the tin got there, but it doesn't matter. This eutectic demonstrates that the temperature must have exceeded 1,000 degrees, which was well above the 300 or 400 we were heating the nickel to. So 700 degrees over a large hotspot is incredible. So how do we weed out all the wrong theories? And I have one particular method because it suits me as a computer programmer, which is to use some software to see how the model behaves given any naturally occurring isotope on Earth, one could almost say in the universe. Any natural on Earth obviously means stable isotopes. And so I'm going to apply this test to some well-known models. The William-Larsen model, which invokes heavy electrons, storms hydrotons, and also electron capture. Iwamura-like captures of alphas, deep Dirac levels, Fisher's polyneutron theory, Barjutov's Erzion theory, and my own theory. But I'll be talking more about my own theory on tomorrow. According to the William-Larsen theory, electrons are conjectured to acquire energy. They become so-called heavy electrons. Sufficiently energetic electrons can be captured by protons to produce neutrons, and the neutrons, being neutral, don't see any Coulomb barrier, and they activate, or they get captured by anything which happens to be in your setup. The trouble is, we know very well that neutrons usually activate and produce residual radioactivity, which we don't see. Whittem and Larsen tried to get around this by saying, oh, but the electrons are very special and they absorb any gammas, in which case they should demonstrate they can absorb the gammas. They can't just make an ad hoc assumption which gets around the objection. They must demonstrate it. They have not done so. Larsen, I think, passed away a few years ago, so it's not surprising he hasn't done so. But I think Whittem's still alive. There are 65 naturally occurring isotopes which have become beta radioactive on capturing a 78 kiloelectron volt electron. And that's long before any protons would capture the electron. Surely there are more electrons which have less than 780 keV than there are which have more. So there are all sorts of secondary effects which are predicted by the theory, which the authors have completely overlooked and they haven't taken account of. The lowest energy such reaction, of course, is electron capture by helium-3, a bit difficult to demonstrate perhaps, but it ought to produce tritium, but the energy required is far below 780. It's actually 19 kiloelectron volts. But there are 65 other similar examples. So there's something drastically wrong with this theory. Storms also invokes electron captures as a kind of multi-body fusion. He assumes that there's a standard structure for the fusion of hydrogen isotopes, which involve the capture of an electron. So the first one at the top, which produces eventually, according to this theory, helium-4, goes via an intermediate hydrogen-4 reaction. But we know that hydrogen-4 normally decays in about 10 to the minus 22 of a second into tritium and a neutron. So the absence of fast neutrons and fast tritons would be very, very obvious. And of course, the fast tritons would then cause secondary reactions. Triton and a deuteron in a deuterated environment produce more fast neutrons. So we expect a lot of fast neutrons. All these reactions are, of course, weakened reactions, which by definition are inhibited by about 20 orders of magnitude. So they're extremely improbable, but Ed Storms, not being a physicist, I don't think appreciates this limitation. Just to make to contrast those reactions with what a nuclear physicist would probably propose without any weak interactions at all. The PD goes helium-3, as I've mentioned. The deuteron fusion goes to tritons and helium-3. 2 protons would produce a positron, which we noticed by the 511 keV annihilation gammas. We don't see these things, so they don't happen. Then Ed tries to get around the difficulty of electron capture because it would produce radioactivity by invoking BOLEPs, which are the so-called bursts of low energy photons. But there's no model which actually explains how you get BOLEPs. He's suggesting there might be thousands, perhaps tens of thousands of gamma ray photons coming off at such low energies they don't escape the apparatus. So again, it's just an ad hoc solution. He suggests that the hydrogen-4 beta decays, and you would expect Cherenkov radiation for that, which again is not observed. I do recommend, if you're doing any electrolysis, that you go into your laboratory at night to see if you can see any Cherenkov radiation. The naked eye will detect it. You don't need any particular apparatus. We don't see the positrons, which usually occur concurrently when there's electron capture, these kind of energies. And multi-body fusion is, quite frankly, not very likely. Positron emission can occur as a competing mechanism, it usually does. So now I want to pass on, we're still discussing Ed Storms, who also invokes Iwamura type multi-body fusion by multiple deuterons. And in this notation, I've used beryllium-8, which corresponds more or less to 4 deuterons. And Iwamura detected this first reaction because he showed that praseodymium-141 could be formed from cesium-133. And it's mildly exothermic, but obviously with 4 deuterons, it's extremely exothermic to the tune of about 55 million electron volts. And many other products ought to be formed because the whole thing would fragment at enormously high energies. But let's take this with a pinch of salt and ask, well, what happens if we get Iwamura type reactions in palladium? Because everybody's using palladium. And the prediction is we get radioactive tin and radioactive germanium with nickel. We don't see these. So I conclude we don't have this kind of reaction. So I don't know how Iwamura got his results, but it doesn't quite correspond to what we observe. We can see what happens when beryllium-8 fuses with every existing natural isotope. There are some 250 such isotopes, and 181 of them are exothermic, and 70 of those 181 produce beta radioactivity. So we expect ubiquitous radioactivity, but we don't find it. got an example here of calcium-40, and I used calcium-40 because Iwamura claims to have a layer of calcium oxide in his system, and we expect radioactive chromium, and again, as I say, we didn't observe it. So now we pass on to Jean-Luc and Muhlenberg's deep direct level model. A deuteron and an electron. I should use your notation of a D bar for this, but I've used more standard notation. It reacts with most palladium isotopes, creating radioactive silver. Again, we don't notice these predictions, so I'm a little bit doubtful about this. And let's pass on now to another question which is frequently raised, which is the heat helium-4 ratio. We saw that graph in Nagel's presentation a moment ago, showing a peak around 23 or 24 million electron volts. Actually, there's quite a lot of variation there. If you examine the graph carefully, it's on a logarithmic scale. So actually a very wide variations are compressed into what appears to be a very narrow band. It's not like that at all. And this would only be significant if only one reaction were occurring. So if there were some reactions, for example, in the light hydrogen system, which were not using deuterium, these would interfere. So I don't think the heat helium ratio is at all significant. We expect multiple reactions. We almost certainly do get them because the Iwamura type fusions, for example, are an example. We don't expect in any circumstances a 24 MEV ratio. There used to be a time when I was a very strong proponent of Fisher's polyneutron theory. The trouble with this, and I think I realized it, but you know, when you get enthusiastic about a theory, you tend to suppress your worries. The thing about this is, if polyneutrons existed and they just passed into some heavy water, which is quite a dense concentration of deuterium, you would expect a runaway chain reaction of the kind we see at the bottom here. N here is a neutron, A is a polyneutron of mass number A, and it just goes on growing and growing and growing and growing, getting bigger and bigger. I think we would notice the deuterium would start boiling away, or the heavy water would boil away. We don't see this at all. As far as we know, heavy water is fairly stable. And Barjutov's Erzion model, which is also rather similar to the polyneutron model, predicts a negative Erzion, and this would react with lithium 7, sorry, an anion, this would react with lithium, which is present in a large number of setups, produce a negatively charged particle. It's in red, which means it's a radioactive particle, and effectively that would withdraw from the system all the Erzions, and because a negative particle, heavy negative particle, would be attracted immediately to any nucleus, and so effectively it would just stop any reaction at all. Even if it decays, it's going to decay in a matter of minimum of seconds, surely. And that, but you know, if you withdraw a particle, a very few number of particles, would take seconds to regenerate. You're not going to get any nuclear anomalies. Oh, so then we have the solution which solves all known problems. It borrows from the Fisher and Barjutov models, and bypassing both the previous objections. And I'm going to present that, I think, tomorrow, so I won't say any more about it. So in conclusion, all models predict residual radioactivity, including my model. If the expected radiation is not found, I say gammas because the gammas are very easy to detect, the model must be refined. Any valid model must make more predictions and assumptions or parameters. This is absolutely fundamental in statistics. You can't predict 2 or 3 reactions if you're going to then invoke dozens of parameters to explain it. And it's not acceptable to ignore established nuclear physics laws for that, some very good experimental reasons. So thank you very much.
Well, you mentioned these radioactive elements. I looked at them. The fact is that they're very short-lived. And most of the time, they're not producing gamma rays. So with beta emission or electron capture, you will never see anything. That's why you don't see. You should check each one of these elements when they produce.
You know I have the software to do these checks, and I have checked, and I'm right.
No, you're wrong.
All right.
The software for that, I think table of elements and with radioactivity.
But you haven't done the test to see how the interactions with.
I analyzed radium.
Yes, exactly. No, exactly, but that's different.
And the silver it produce is very short lifetime, and there's no gamma production after that.
So there should be prompt gammas in that case. If they're short-lived, there should be almost prompt.
So it could be electron capture. You would not see anything.
Okay. I think at the final session we can discuss this again. I'll try and find some data. In fact, in the meantime.
My issue with my observations and reviewing a lot of historical documents is that there seems to be a penchant for looking at things as two-body interaction. And this was the way that Matsumoto began. And in 2001 in fusion technology, he admitted it was millions and millions of neutrons that acted together in an electronuclear collapse. And this is what IWAHLM14 found, and he called it electronuclear macro cluster. And it also was Leclerc found with his partner using both laser stimulated cavitation and sound stimulated cavitation, where you've got very, very large numbers of neutrons into some sort of quasi-electronuclear macro cluster. They collapse and you have a stellar type alpha conjugate nuclei product coming out. So these debates about, and when you do the reaction table, you get what he observed in 1990 in displaying neutron, the actual fission product, and they're all anetronic. You get the varying number on both sides the same, and you just have a physical one-pole matter that's coming out with kinetic energy. And you get the heat, but a lot of the products are helium. So I wish people would talk about cluster decays and large bodies of matter interacting.
Okay, let's talk about this privately later,
yeah.
or even in groups.
Yeah. Okay, because the flow energy
this interface between atomic physics and nuclear physics is very strong. Okay, so this first point. And what I want to say more, you are speaking about this radioactivity and short-living isotopes. But if the short-living isotopes are there, that it means that they are very, very intensive if you look at for the decay, because the number of decaying gammas is much higher and it is much easier to detect that compared to long-living isotopes. Okay, so this not we should see some gamma. Okay. So, and the next point, this argument about PD reaction. The cross-section thermal energy depends very strongly on the screen energy. So the screen energy is, let's say, about, I don't remember exactly the numbers, but we can look at our publication. It was 13 to 14 years ago. They calculated for different screen energy already there. And the PD reaction cross-section is higher than VD only for very low screen energy, not for high. For high energies, for high screen energies, VD reaction is much stronger. So the conclusion that is a special number, let's say 10 to 14, it is not correct because it depends very strongly on the screen energy. Okay, so we can discuss it and this important conclusion. This in any case, if I discuss about electron resonance in the reaction, it depends also very strongly on screen energy. So this is very strange, but very simple physics. Okay, and we should include it in our predictions, in our discussions.
Following this away the question of shampoo, I think that we have to watch people about reaction that apparently doesn't reaction like electron capture. So maybe it's a way to just an idea.
Direct question for Conrad. How do you explain the sort of observations of palladium producing or titanium or whatever is in the Lennon reactor producing a spread of elements that typically either find if they're light elements or look like fission in the lower
This,
lower.
you are asking about concentration, and it's very difficult to explain physically because you need some processes that can produce something like fission, or you can speak about many neutrons that are tested and produce different items. But from simple nuclear physics is not so difficult to understand. And what is important to calculate the cross section for the multiple Electron Capture. The cross section is so low that it's not easy to understand the process. Maybe somebody can come and say, I can calculate it and show the case. But in my opinion, there are some problems from the experimental point of view. Because usually there are some contributions, components, of ingredients of your sample. Even you use so-called pure samples, you have some constituents, some isotopes that are inside of the sample, and then if you keep the sample, you have a diffusion that is diffusion which is can be very different for different isotopes of the same element. There are very nice examples, for instance, for enhanced diffusion of oxygen 18 compared to oxygen 16. position 18 goes to the center, and then you measure unusually high amount of position 8 and the surface. Simple because of this diffusion. So from the external point of view, it's not so easy to measure it. So you measure different elements, and it is, I don't know.
So I would refer you to the work of Escalator, 609 years of experiments in the isotopes laboratory outside of here. 300 joule discharges into ultra pure pin targets with an ultra pure accretion bit. And there were a whole lot of nearly pure lead or 86% gold or like these were basically not even present. But they were low even different.
The question is you measure surface from the bulk. If you measure the bulk, the large depth distribution.
Yeah, so they used iron ablation and they cut down and they showed that they went through. And if you, because of the orientation, you have the impact and then you have things spreading out from the impact. Yeah, it's not contaminated. That's why they have it treated.
There can be an opportunity to involve the alien with us. Lord, you explain what if you make arc with carbonate causing water, you get some iron.
Iron and the rest of the periodic table.
I can speak to that as well. So, Bocchus and Sundaresan in the 1990s, they did carbon arc discharge underwater. And they found that they got iron, and they said it was 2 carbon, 2 oxygen, go to 4 helium and iron, 54 or something. The other idea is you get synthesis of aluminium from, I think it is carbon and nitrogen, and it's dissolved in the water, and then you get 2 silicon, 2 silicon, fuses to iron 54. My understanding now is that the oxygen is important. They identified that. What they did was they boiled the water to remove the oxygen, remove the nitrogen and the oxygen. They then oxygenated it, and they found that they synthesized iron. When they did the opposite, they removed all the gases from the water and they saturated it with nitrogen. They didn't see any iron production. Okay, and I believe that's because oxygen is uniquely paramagnetic. And anyway, we get into magnetic monopoles, and they allow the clustering that forms the material.
But the material balance takes no doubt.
Oh, absolutely, and it becomes. I've seen the synthesis as well. Yeah, anyway.
Okay, I think that's the end of the session. See you tomorrow. And supper, of course, is at 7:30 downstairs. Dinner tonight is at 7:30.